Welcome to today's webinar. The topic today is design of code-formed sections in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Jonas, but my two colleagues can introduce themselves.
I would also like to welcome you to today's webinar. My name is Sonja von Bloh, and I will be the presenter today.
Hi, and my name is Jonas Bien. I'm working as a product engineer at Dlubal for now almost a year, and I will try to answer the questions along the webinar as best as I can.
Okay, thank you. Then we can switch off our webcams that the attendees can see the full screen. Before I hand over the screen to Sonja, I would like to say something about how you can ask questions, at least for the attendees who participate the first time. You can show the panel with that arrow here, and then you can enter your question here, and we will answer you. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, now I hand over the screen to Sonja. Sonja, it's your turn.
The topic of this webinar is the design of code-formed cross-sections in steel design with warping torsion. I will design the code-formed set purlins of a steel hull that you can see here in the image to the right. Today I will first show you how to model special sections in RSECTION and how you can import these sections into RSTAB. In the next step, I will show the settings to be made for the warping torsion analysis and go into the rotational restraint and the shear panel. Finally, I design the purlins in add-on steel design. The code-formed cross-section that I want to use is not included in the RSTAB cross-section library. Therefore, I will create this cross-section in RSECTION. The cross-section geometry is available as a centerline model in DXF format so that I can use the import function. I start here the import via File, Import, DXF. Then I choose the corresponding DXF file and then I click on Open. In the import dialog, I select the option to create the elements via the center lines, and I define here a thickness of 2 millimeters for them. The creation of cross sections based on DXF files was the topic of a previous RSECTION webinar. You can find this webinar on our website or on YouTube. Furthermore, I have to define the material here. I just want to use this material that's already shown here, but if I want to use a different material, it would be possible to open the material library and select the material from this library. Okay, click here on cancel. Then I start the import process and click here on OK. With this import function, the part is created automatically, and also the elements are created automatically that you can see here. The elements are required for the calculation using the thin walled analysis and for the calculation of the effective cross-section. I now want to go into the base data, and here I choose the analysis method. Here two analysis methods are available, the finite element analysis and the thin walled analysis. I choose here the thin walled analysis. As already mentioned, elements must be defined for this. this setting only affects the default setting in RSTAB. If necessary, I can change the analysis method in RSTAB. Furthermore, I activate here this add-on effective steel section, and I choose the standard Eurocode 3 part 1.3 for cold formed cross sections. This setting is necessary so that the steel design in RSTAB is carried out according to the standard for cold formed cross sections. Then I click here on OK. It's also possible to dimension the cross section. I will do this. For this, I create a new dimension, and then I choose here the corresponding points. And these dimensions can be displayed also in RSTAB. In our section, I can also calculate the effective cross-section and the stresses. This is useful, for example, for a preliminary design. This has been demonstrated in previous webinars, so I won't go into it today. However, it makes sense to start the calculation once to find any modeling errors. I will do this. Here I go to calculate all, and no error was shown, so it's possible to import this cross section into RSTAB. Then I save this file. Click here on Save, and I will save it in this directory, and then I can switch to RSTAB. I have already created the steel hull in RSTAB. The purlins consist of the cross section just created in our section. For now, I have assigned this cross section to them, and I want to modify this cross section. For this, I open the Edit Section dialog, and then I open my cross section library. And then I want to import my created cross section in our section. And the folder in which the R section cross section is stored must be integrated into the Dlubal Center. It's only possible via the Dlubal Center to import a cross section from our section. And I want to put this folder directly under the project. So I check, choose Add Existing Project here from the context menu. And then I choose my folder. It's here on the desktop. And then I click on OK. The folder is now linked to the Dlubal Center, and I can select the R section cross section. It has recently become possible to import multiple cross sections in one step. For this, I have to select this cross section, and then I can click on OK, and all the selected cross sections will then be imported into RSTAB. Now I only want to import this cross section, so I click on OK. Here the checkbox thin-walled model is activated. This setting was taken from the chosen analysis method in our section. However, I can also deactivate this option here so that the calculation of the gross cross-section properties is then carried out using the finite element analysis. If this option cannot be selected, then no elements are defined in the R-section cross-section. You can see here in the graphic of the cross-section that the dimensions are shown. These are the dimensions I have created in our section. And I click here on OK. For cold form set cross-sections, the center of shear lies outside the cross-section and the main axes are rotated. Usually, the loads don't act on the shear center, which results in double bending and torsion. Usual lateral torsional buckling checks cannot be carried out. Eurocode 3 Part 1.3 includes design methods for cold form set purlins, but the purlins must be within certain limits. These simplified design methods are not implemented in steel design. The lateral torsional buckling of any purlin can be carried out according to the second order theory, considering warping torsion and the use of equivalent imperfections. I would like to show this approach today. And for the calculation considering the warping torsion, I first activate the add-on warping torsion in the base data. For this, I go to the base data, on top add-ons, and then I activate this checkbox here. Warping at the member ends is assumed to be unhindered by default. To transfer the warping between members that are connected, you can define a set of members. The frames consist of several members. You can see it here. These members are divided, and this means that there are warping releases between each member. The warping should be continuous for the frames, so I've already defined a set of members for them. I show you this in the wireframe model. Here I've created the set of members for each frame. And if I open the edit set member set dialog, then you can see here a checkbox discontinuous torsional warping. This option controls whether the warping should be transferred or not. This is supposed to be transferred, so I don't check this checkbox. Furthermore, the purlins are divided at the connection point here with the purlin suspensions, and the warping should be continuous for the purlins. So I've defined set of members for the purlins too. You can see it here. When calculating with 7 degrees of freedom, the connection of members is always assumed to be at the center of gravity. If the connection is to be made at a different point, you can use member eccentricities, or you can also model the connection with rigid members. In the steel hall, I have already defined members eccentricities for the transoms, the purlins, and the purlin suspensions. To do this, it's necessary to activate the checkbox eccentricity in the member dialog. I have done this here for the suspension. Here I've activated this checkbox eccentricities, and here in the tab eccentricity, it's possible to assign a member eccentricity to this member. And I want to also look into this definition of the member eccentricity. You don't have to calculate the eccentricities manually. you can also define them relative to another cross-section. I have used this option here. I have defined the eccentricity type relative to sections, and I have defined a transverse offset from the section of another member, so that the eccentricity is calculated automatically via the program. The steel hull is covered with trapezoidal sheeting. I would like to use the trapezoidal sheeting as lateral and torsional support. I can take this stabilizing effect into account in RSTAB using shear panels and rotational restraints. I first define the shear panel. I can do this via the navigator data. Here under types for members, I see here member shear panels. I create a new one. And there are different types of shear panels to choose from. We have here the trapezoidal sheeting or a bracing, or trapezoidal sheeting and bracing. I want to define a trapezoidal sheeting, so I choose this type. Then I go to the tab trapezoidal sheeting, and I choose the trapezoidal sheeting from the library. I go here, and then I define this trapezoidal sheeting. It's a Hirsch T5175. I click on OK. The trapezoidal sheeting is fastened in every rib, so I choose this option here. And the shear panel length corresponds to my roof length, and I can pick this graphically. I choose here measure, and then I choose my nodes, and now the shear panel length is defined with 10.05 meter. Then I have to define the beam spacing. I will do this also graphically. I measure this, and it's the spacing between the purlins, and then I click on OK. Next, I define the rotational restraint. I find this also in navigator data here. I create a new member rotational restraint. There are also different rotational restraint types, continuous or discrete. For the trapezoidal sheeting, the restraint type is continuous. Then I go to the tab continuous. The trapezoidal sheeting and the material can then be selected from the database. The purlin spacing and the continuous beam effect still need to be selected. The spring stiffness C100 must be determined depending on the load. Unfortunately, the effect of cross-section deformation on rotational restraint here can only calculated for I cross-sections, but not calculated for R section cross-sections. The calculated spring stiffness would therefore be on the unsafe side, and I have determined spring stiffness manually according to the formulas described in Eurocode 3 part 1.3. And I would like to consider the spring stiffness. So I go back to the tab main, and then I choose here the type manually. And then I define the rotational spring stiffness. I've calculated it to 1.07 kilonewton meter per meter. I click here. I now have to assign the shear panel and the rotational restraint to member supports. I'm creating a new member support. I will do this also via the navigator data. And here I create a new member support, and then I choose my shear panel in Y and my rotational restraint about X. The trapezoidal sheeting lies on the top of the purlin, so I define an eccentricity, and here I define the reference on the top here. Then I go to the tab shear panel in Y. Here I choose the shear panel type I've just created, and I will do this also for the rotational restraint. Here I choose the manually defined rotational restraint. I now assign the member support to the corresponding members. To do this, I click here on Pick Members, and I use visibility for it. Here I use a generated visibility. I choose it here, the cross-section of my purlin. Then I activate the visibility, and then I choose here my members. Then click on OK and OK, and then the trapezoidal sheeting and the shear panel are assigned to these members. It's also possible to display the rotational restraint and shear panel graphically. To do this, I go to the navigator display, and you can find the checkboxes here under types for members. And here I activate member shear panels and member rotational restraint. I will see it if I cancel the visibility mode. Here you can see now the shear panel and rotational restraint graphically. Okay. I can uncheck this checkboxes again. I don't need it now. By default, rotational restraint and shear panel are not taken into account in the static, stability, and modal analysis. I can also take these into account in these analysis by using a structure modification. And I want to create this structure modification. I find it in navigator data here under special objects, and here I define a new structure modification. The consideration of shear panels and rotational restraints is already activated here via this checkbox, and then I modify here the name of this structure modification. I name it consider shear panel and rotational restraint. And then I click on OK. I then have to assign this structure modification to the relevant load cases or load combinations in which it should be taken into account. For this, I use the combination wizard. I find this combination wizard in navigator data, and here I open this combination wizard, and the only thing I have to do is to check this checkbox, consider structure modification, and to choose the corresponding structure modification. And then I click on OK. I've defined already dead load, snow load, wind and X direction and Y direction. I will show you this. For this, I activate here the view. Here I've the load case self weight, then snow, and also wind in X direction and Y direction, and also a pre-stress on the bracings. I want to go back to my loads that I've applied on the purlins. If a member load without eccentricity is defined, the load always acts at the center of gravity in the calculation with 7 degrees of freedom. I will go into this load, and here I have the possibility to define an eccentricity. If the load acts on another position, it's possible via an eccentricity to change this. And I've activated here the eccentricity checkbox, and in the force eccentricity, it's possible to define the eccentricity for the loads. The eccentricity should, the load should act on the top of the cross section, so I've defined here the reference on the top. Click here, okay. I've already created global imperfections. I will show you this now. I've created global imperfection in plus X direction and also in plus Y direction. And I now have to define the initial bow imperfection for the purlins. Various options for defining imperfections have already been demonstrated in previous webinars. Today, I would like to show the definition of local member imperfections. The purlin is here supported in a Y direction by the purlin suspension, so that a two-wave imperfection shape would be possible. If the suspension is not stiff enough, it would be also possible that you have a single wave imperfection shape. For the imperfections, I could now create two imperfection cases. However, it's also possible to use a stability analysis to obtain information about the imperfection to be applied and thus reduce the number of imperfection cases. I would like to show this now, and to do this I go to my navigator data, and then I go to base data, and here I activate the checkbox structure stability. Then I click here on OK. I first look at the stability analysis settings. To do this, I open this here. And I assume that local mode shapes for the purlins only appear at higher eigenvalues. Therefore, I increase the number of eigenvalues to be calculated to 25. In the combination wizard, I activate the stability analysis with the calculation of 25 eigenvalues, and I also change my static analysis settings to first order theory. And then I name this wizard stability. I open now the design situations, and here the combination wizard stability is already chosen, and now the load combinations are generated with considering of the global imperfection, my structure modification, and my structure stability add-on. I now run the calculation for my design situation 1. A message informs me that the cross sections or topology of the members in the member set are not compatible, and the warping may not be able to be transferred. The reason for this is, among other things, that the set of members of the frame is not straight. You can see it here. The column is here angled to the other frame, and this is the reason for this warning message. I assume that the warping can be transferred through the connection, so I ignore this warning message, and the warping is then transferred. Here on the overview, I can see that the minimum critical load factor is calculated in load combination 3. I will go to the stability analysis, and I will open now the load combination 3. I deactivate here the display of the loads. As a part of the stability analysis evaluation by mode shape, the mode relevance factor can be used to quickly differentiate between local and global mode shapes. A modal relevance factor of 100% means that a single member has maximum relevance for the considered mode shape. To look into the mode relevance factor, I open a different table. Here, results by member, and here effective lengths and critical loads by member, and you can see here this mode relevance factor for all members. I can also use filter option to output only mode relevance factors that are greater than a certain value. I will do this now. Here I open the result table manager, and I activate this checkbox according to criteria. And here I can choose the mode relevance factor. And here I want to see only mode relevance factors that are greater than 70%. And I click here on OK. And then I want to see here my member number 258, and this member has a mode relevance factor of 100%, and this means that is a local eigenvalue. And I can see for this also the mode shape, and this is a single wave here for this purlins. So I have only to define a single wave shape for the bow imperfection. I will do this now. And for this, I create a new imperfection load case. To go this, I open the navigator data again, and then I create here a new imperfection case. I name it imperfection and plus y direction, and I choose here the imperfection type local imperfections. I now have to define the local imperfections, and I define a new member set imperfections. And here I choose the imperfection type initial bow. And as definition type, I choose manually relative. And for the Z cross-section, I use according table 6.3 of Eurocode 3 part 1.3, the buckling curve B, so that I define an initial bow of 1 divided by 250, and I want to assign this initial bow to the imperfection direction Y. Now I have to choose the member sets, and I activate here my visibility once again. I choose then the member sets, and I click on OK. I can show this also graphically if I activate the Show Imperfection button, and I now have to define the imperfection also in the opposite direction, and I will do this by copying the imperfection case, imperfection and plus y. To do this, I go to the navigator data again, and I open here my imperfection case. I choose it, and then I click on button copy selected imperfection case. I rename this case, and then I click on OK. And all I have to do is now to change the imperfection direction to -y. I would now like to combine the imperfections with each other. For the combination of imperfections, I create a group of imperfection cases, and I will do this here in the Edit Imperfection Case window. Here I create a new imperfection case from imperfection type group of imperfection cases, and I want to combine first my imperfection in global X direction with my imperfection in plus Y direction. For this, I go to the tab group of imperfection cases, and then I create a new line, and here I choose imperfection in plus Y with the operator and imperfection in plus Y, and I name it imp plus X plus Y. The other imperfection, I create the other imperfections with by copying. So I select this group of imperfection, and then I click here on copy selected imperfection cases. And here I change the parameters to -y, and I need this also for the global direction Y. So I copy this. And all I have to do is to change here the name and the imperfection. So that the individual imperfections are not taken into account in the combinatorics, I deactivate for them the checkbox active, and then I click here on OK. Then I have to modify my combination wizard, or to create a new combination wizard for my design situation. For this, I open the combination wizard dialog and I copy the stability wizard and I name it here design. And I want to do my design according to the second order theory. So I choose here a second order. I don't want to use the stability analysis anymore. And I want to consider my imperfection cases and my structure modification. Then I click on OK. I now have to assign this combination wizard to my design situation. For this, I added my design situation, and here I choose now the combination wizard for the design. If I go here, then I can see the results for my load combination. Here, the imperfections are considered, and also the structure modification. The structure is complete, so that I can make the settings for the steel design. For this, I first activate the steel design add-on in the basis data. In the base data, here on tab add-ons, I activate here the steel design, and on the tab standards, I select the standard that I want to use. I select here the Eurocode 3, and I select the German National Annex. And click then on OK. I now want to look into the ultimate configuration for the steel design. I find it here also in Navigator Data, Ultimate Configuration. And here I deactivate the checkbox Perform Stability Analysis, since all stability effects are already included in the calculation. Therefore, only cross-section checks have to be carried out, but with the partial safety factor gamma M1 for stability designs. For this, I have to activate this checkbox. Here in chapter Design of Cold Form Sections, the steel design derives from the manufacturing type, whether the design must be carried out according to Eurocode 3 Part 1.1 or Eurocode 3 Part 1.3 for cold formed cross sections. If I deactivate here this checkbox perform designs of cold form sections, then the design would be carried out according to Eurocode 3 Part 1.1. Then I click here on OK. In the table steel design and of the add-on steel design in tab Objects to Design, I choose the members that I want to design. I want to design all purlins. I deactivate here this checkbox member sets, and then I choose here the purlins. I activate the visibility first, and then I select all my purlins, and then I click on OK. The calculation takes time because the effective cross-section is calculated in an iterative process. I therefore show you the results in a calculated model. And here I go to the design ratios on members. In the table, the numerical results of the design are shown to display the details. I double click on the corresponding table row. Separate effective cross sections are calculated for axial force, major axis bending, and minor axis bending. According to the information from the Standards Committee of Germany, the effective cross-section can also be calculated for the combination of internal forces in a design with 7 degrees of freedom using imperfections. We will implement this in future. The effect of distortional buckling is determined using the eigenvalue method. You can display the mode shape via this button here, section information. And here we have the buckling shape for only axial force, for major axis bending, and for minor axis bending. I will show you here the buckling shape for only axial force, and by default the mode shape for distortional buckling with the associated critical load factor that you can see here is displayed first. By clicking here on the point on the graphics, further forms of instability can be displayed. Here you see instability form for local buckling. Okay. The stresses can also be displayed graphically. To do this, I open here the result diagrams and sections. And it's possible to display stresses on the gross cross-section, and it's also possible to display stresses on the effective section. If I want to see the effective section due to minor axis bending, I choose here this setting, and I can now see here this element is reduced due to local buckling, and here the lip is reduced due to distortional buckling. The elastic design according chapter 6.1.6 is carried out. The utilization is below 1 for all purlins, so that the cross-section and stability checks are fulfilled. That brings me to the end of the webinar. I hope it helps you in designing cold-formed cross-sections and steel design. I now give the floor back to Andreas.
Okay, thank you, Sonja, for this nice presentation. We got some questions. One question was if we can, or if it is possible to exclude, for example, the restraint for certain load combinations. For example, when we have got a very high wind suction. Yeah, that's of course possible. We can use different structure modifications for the different load combinations. But yeah, in our example, it was not necessary because we have a higher self weight minimum. It's the same as the wind suction, our example, but that would be possible. Okay, then before I would like to show you where you can find the recording and the models, I share my screen. So just a moment. So I hold back. Yeah, before I show the website, just a small hint. If you want to get a free product demonstration or something like that, or you would like to get a non-binding offer if you want to buy the program or an add-on, just contact our sales team with that link here, or you can scan the QR code. You can download the PowerPoint slide from the website. I show the website, just a moment. Our website is dlubal.com, and under news and events, here in the middle, you find the webinars. We record all our webinars, also today's webinar. Those are the future webinars: construction stage analysis, seismic design for reinforced concrete, and so on. That's our new add-on, time history analysis, and the webinar takes place on 16th of November. So that's today's webinar. In the next days, you will get an email with a link directly direct to that page, and then you will find the recording in the middle. You can already find the presentation slides and the DXF file that Sonja has been used, and the models can you already download. Okay, that's also all from my side. Thank you for your attention. Thanks to Sonja for the presentation. Thanks to Jonas for answering the questions. Yeah, I hope we meet each other in the future webinar. Yeah, I wish you a nice rest of the day. Bye-bye.